Okay, so once again, good day everyone. Our topic for today is about concurrency, deadlock, and starvation. So it covers the condition for deadlock. No? So after studying this lesson, you should be able to list and explain the conditions for deadlock, define deadlock prevention, and describe deadlock prevention strategies related to each of the conditions for deadlock. Explain the difference between deadlock prevention and deadlock avoidance. Understand two approaches to deadlock avoidance. Explain the fundamental difference in approach between deadlock detection and deadlock prevention or avoidance. Understand how an integrated deadlock strategy can be designed. Analyze the dining philosopher's problem, and explain the concurrency and synchronization method used in Unix, Linux, Solaris, and Windows. So when two trains approach each other at a crossing, both shall come to a full stop, and neither shall start up again until the other has gone. So in this discussion, we examine two problems that flag all efforts to support concurrency processing, so deadlock and starvation. So we begin with the discussion of the underlying principle of deadlock and the related problem of starvation. Then we examine the three common approaches for dealing with deadlock: prevention, detections, and avoidance. And we then look at one of the classic problems used to illustrate both asynchronization and deadlock issues, the dining philosopher's problem. So, of course, deadlock can be defined as a permanent blocking to a set of processes that either compete for system resources or communicate with each other. So a set of processes is deadlocked when each process in the set is blocked awaiting an event. No, typically the freeing up of some requested resource. No, that can only be triggered by another blocked process in the set. So deadlock is permanent because none of the events is even triggered. Unlike other problems in concurrency process management, there is no efficient solutions in the general use. Okay, so to give us more details about the topic, let us all welcome our presenter. Go ahead.
Good morning, sir. Good morning, classmates. This is my report. Deadlock and starvation.
So if you have some questions related to the topic, do not hesitate to post your question in our chat box.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Today, inshallah, we are going to review, discuss the key points of chapter 6, which is concurrencies, deadlock, and starvations. Okay, so the learning outcome for this chapter, we have 6 learning outcomes. The first one is what is the difference between reusable and consumable resources, and how to sketch a resource allocation graph. And then deadlock preventions along with its conditions, sufficient and necessary conditions, how to avoid the deadlock detection and recovery. So this one is pair. When you have detection, you have recovery. And we are going to discuss on the dining philosopher problems. Okay, so deadlock prevention is conservative. Okay, deadlock avoidance is in between. You have two types here: process initiation denial, okay, and resource allocation denial. Okay, and then the most liberal thing is detection. So it allow the to hold the resources, but once in a while it will detect whether the deadlock has happened or not. Okay, so let's go to the first learning outcome, which is the consumable versus reusable versus consumable resources. Okay, so as you can see here, we have reusable resources. So what is reusable resources? It can be safely used by only one process at a time, okay, and is not depleted by that use, so it will not be go away. It can reuse, okay. For example, the processors, the I/O channels, network, printers, USB, okay, main and secondary memory. Main memory, secondary is the hard drive, the devices. It can be reused, okay, and even the data structures, files, database, and semaphore. So this is reusable resources, okay. So what about the consumable resources? The consumable resources, the key point here, it can be produced and it can be destroyed or consumed, okay. For example, the interrupts, okay, you generate the interrupts, okay, then it can after it's finished, then it goes. Signals like some the signalings, okay, and message, okay, and information in the I/O buffer. So this is the consumable resources, okay. So I hope you understand the difference between reusable and consumable. So let's move on to the next learning outcome, which is the sketching of resource allocation graph, okay. It is easy, okay. There are two basic operations, okay. The first one is request, okay. So what you can see here, you have the circle here is the process, okay, and the box here is the resources, okay, and the dot here is represent how many resources that you have. For example, you have one printer, you put one dot. If you have two printer, then you put two dots, okay. So this is just request, okay. It's not necessarily granted or held by, okay. So when you get held by, you can see the arrow is pointing from the dot here, dot the inside the resources, okay. So there's only two operation here, request and held by, okay. The circle is process and resources represented by the box or square. Okay, to formulate, okay, so we have several important metrics here. Resource R, matrix R, R1, R2, Rm. R1 means the type of resource number 1, resource number 2, and resource number M. V is the availables, how many is available currently, okay. So V1, V2 until Vm, okay. And then the claim matrix is the required resources, in order to finish the process, then the process need to have several resources, C11, C12, C1M. So this is process 1, process 2, and process N, okay. So you have resource 1 until resource M, and you have process 1 until process N, okay. And then you have allocation matrix from the claim, then how many from the required here, from the claim, how many have been allocated, okay. Then you can see how many will be left request. So we have matrix Q, which can be calculated, the claim minus the allocated already, okay. So the same thing here, across the column you have the resources, and across the row here you have the process. Now let's see in example. So for example, you have matrix R here, okay. This is the resources. So R1 you have 2, R2 resource 1, R3 is 3, okay. So you have 2, 1, 3, okay. For example, you have 2 gigabytes, 1 hard drive, 3 printer, for example, okay, just an example. And then you have 3 process, 1, 2, 3, okay. And this is allocated. The V can be calculated if you know the allocated. So how? So you just add this, okay. You add this one, 1 plus 1 is 2, 1 and 2, okay. So 2, 1, 2 here, okay. And then the V is the total resource, 2 minus 2 is 0, 1 minus 1 is 0, and 3 minus 2 is 1, okay. Then the claim matrix will be given, okay. C is here, and the Q can be calculated from the C minus A. So C Q will be C minus A. So you can see here 1 minus 1 is 0 and continue, okay, until the last one. 0 minus 0 is 0 here, okay, from here until here, okay. Now how can we draw the resource allocation graph, okay. So here is the request. So you can see here this first part, okay, and here is the allocated, or you can say here this held by, okay. So you need to see these two metrics, the matrix A and matrix Q. So the first one, we know that we have 3 process 1, process 2, process 3, and then we have 3 resources. And see here, resource number 1, you have 2 dot because you have 2 here. Okay, you have 2 here, and resource number 2 you have 1 dot only, and resource number 3 you have 3 dot. Okay, then from the matrix allocation you can see the red arrow here. Okay, so for example, P1 allocated resource number 1 and resource number 3. Okay, resource number 1 here, okay, and resource number 3 here. Okay, resource number 1, resource number 3, and continue. And the request all is 0 except for P2 here. This is P2. What is request? Request resource number 3. So request, you can see here the arrow is go to the edge of the box. Okay, so I hope you understand how to sketch a resource allocation graph. Basically, two important metrics here, matrix A and matrix Q. Okay. Okay, now let's move on to the deadlock preventions. Okay, let's discuss on the deadlock preventions. So what is deadlock? So we have necessary condition and sufficient condition. So necessary conditions mean you have possibility of deadlock. Sufficient condition mean the deadlock is confirmed or it's already deadlock. Okay, so the necessary condition to have a deadlock, you have mutual exclusion, which is only one process may use a resource at a time. Hold and wait, a process may hold allocated resources while awaiting assignment of others. So for example, process 1 requires resource number 1 is 1 and resource number 2 is 1. Okay, so it get hold of 1, so it will hold this one first before it get the resource number 2. Okay, so this hold and wait. No preemption mean no resource can be forcibly removed from a process holding it. So for example, this one is still waiting for R2, we cannot preempt this one. Okay, resource number 1 that get held by the P1. Okay, and circular wait is a closed chain of process exists such that each process hold at least one resource needed by the next process in the chain. So if you remember the traffic jam in the intersection, you have something like this. Okay, you follow you create a circular loop. Okay, circular wait. Okay, so what is deadlock prevention? Deadlock prevention is try to prevent the conditions. Okay, so you have two types here, which is the first one is indirect. You are try to prevent the number 1, number 2, and number 3 here, and the second one is direct, which is you are trying to prevent the circular wait. Okay, so this is deadlock prevention. Remember that this one is conservative. Okay, deadlock prevention is conservative. It try to block as much as it can to avoid prevent the deadlock. Okay, but let's see in more details. As we know from the previous chapter, mutual exclusion cannot be disallowed. Why? Because we need mutual exclusion. Otherwise, if you remember, while Microsoft Word printing and then Excel printing, so you have half of printed page. Okay, so you want to have mutual exclusion exclusively for one program that get hold of the resources. Okay, hold and wait, this one can we can do hold until got all resources, but this one is inefficient. Okay, no preemption, we can allow selected preemption. So only this one I think is possible. So no preemption mean we just allow selected preemption. Okay, and then the last one is circular wait. So we define a linear ordering. This one is again inefficient. Okay, so due to this one, normally we don't use this one because this is too conservative. Okay, this is too conservative. It try to prevent as much as it can. Okay, while we are only this one we can do. Okay, so then we come to the next one, which is deadlock avoidance. We have two types of deadlock avoidance. The first one is process initiation denial. So basically what the algorithm said, we allow a new process Pn plus 1 only if the resources can handle. Okay, I repeat, we allow a new process if the resources can handle the new claim plus sum of all previous claim. Okay, so we start a new process only if the resources can handle. Okay, if not, then we don't allow. Okay, so for example here, so in this algorithm we just only matrix R and C, as you can see here, R and C only. Okay, so matrix R, for example, you have 2 1 4. Okay, matrix C is 101 or 101 010. Okay, and then let's see here. If I have P4 010, okay, is it allowed or not? Okay, if you add this one, so this is 2 1 2, okay, you add with this one, become 2 plus 0 is 2, 1 plus 1 is 2, 2 plus 0 is 2. So this one is bigger than the available resources, at least under R2. R2 here cannot cope. Okay, you cannot have more than 1. Okay, you can see here R2 is only 1. Okay, so what is the answer? The answer is no, you cannot start P4. Okay, but what if we have another P4? We have 0 0 1. Okay, so when you add here, become 2 1 3. Do you allow or not? 2 1 3, you can see here, still can allow here. Okay, because this is 4 and this is 3. Okay, so you can allow this process. Okay, now the last one, what if we have another request, P5 now? Now we have P5, allow or not? Just check here. Request only, the claim is only for resource number 3. Okay, when you add all together, this one become 2 1 4, and this is exactly the same like this. So you can see here, larger than or equal to. Okay, so this is also allowed. Okay, so but this one is inefficient, because this one is rather inefficient, because why? Because normally during the execution of the process, not all requires all claim at the same time. So maybe it requires this one first and then the next one, not all together. Okay, so for example, you want to have memory first, then you can print, for example, or you can have memory first, then yeah, or you can have here another one like Ethernet card and so on. Okay, Ethernet communication and so on. Okay, so this is a bit inefficient. Okay, restrictive. So we have another algorithm which is called Banker's algorithm. Okay, so the second one is called resource allocation denial. Okay, or this is called also Banker's algorithm. Okay, so it's like a bank, so you will not withdraw money that you do not have in your account. For example, your account have only 1,000 ringgit, you cannot withdraw 2,000 ringgit. Okay, so let's see here. So the same thing, we have matrix R, which is the resources, then allocated. Okay, the one that has been allocated. So we have, for example, 4 process here, P1 P2 until P4. Okay, you can add this one, allocated already 9. 1 plus 6 plus 2 is 9. 1 plus 1 2, so we have 9 2 5. Okay, from here we can calculate available matrix. Calculate available. What is matrix available? Okay, and remember that this is the only dynamic matrix here. Okay, this is always change. Okay, so this is the dynamic variables here. Okay, so you can see here 9 minus 9 is 0, 3 minus 2 is 1, 6 minus 5 is 1. Okay, so you can calculate the available matrix. Okay, then of course we can have this one will be given claim matrix. Okay, and this is the request matrix. So we need to calculate the request matrix. So how to calculate request? Request is C minus A. Okay, so this is the request, which is the claim minus the allocated. So you just minus here, 3 minus 1, for example, 2 minus 0 equal 2 and 2, so you can continue until the end. Okay, so this is Q equal to C minus A. The request matrix equal to the claim minus what has been allocated. Okay, then what the algorithm do? Okay, so for convention we will check the request. So check the request with the available. Okay, so the essence of the Banker's algorithm here, check request. Okay, so you need to check request with available. Okay, can you withdraw 1,000 ringgit? So it will check first whether you have 1,000 ringgit or not. Okay, so the first one is check Q P1. Okay, so you can see check request of P1. Request of P1 is 222. Okay, then available is 011. Of course you cannot allocate because you don't have that much resources. Okay, so this one is not selected, the first one. Okay, and remember by convention we will check from sequentially from P1, P2, P3 until Pn. Okay, the last one. Okay, So let's see the P2. So QP2, the request of P2 is 001. So available is 011. So this one is selected. Okay. When it's selected, then it can run. Okay. When it runs, then the available matrix will be available matrix request. It will fulfill the request. Okay. So it will fulfill the request. Then you can see here just the normal matrix abstraction. The V is 011 here, and the QP2 is this one 001. Okay, so this is the new available matrix, and remember that this is dynamic. Okay. Okay, the next step, when P2 is finished, it will return all the resources. Okay, when P2 is finished, it will return all the resources. Okay, so you need to add again the available matrix will be available plus all the claim P2. What's the claim P2? 613 here. So 01, or which V? Okay, not this V, okay, but this V. Okay, so V plus CP2 010 plus 613, so you have 623. Okay, then as we continue, we check the next one. After P2, we check P3. Actually, you can go back and check P1. Okay, but just for our convention, we just do sequentially from P1, P2, P3 until Pn. Okay, then I finish, then we go back. Okay, check QP2, P3. So QP3 is 103. Okay, we don't check with this V. Okay, we don't check with this V. Okay, because we have the new V here. Okay, so that's why new V, not the old one. Where's the old one? This is the old one. Okay, so you check QP3 with the V. So P3 here is 103. Okay, and available is 623. This one less than or equal to, then selected, then repeat the process. You tend to the request, allocate to the request, so you have the new available matrix, and then after it's finished, then it will return all the resources, and then you have the new available matrix. Okay, then check Q P4. Okay, remember, not the new V, not the old one. Okay, not this one. Okay, even not this one. Okay, not this one, but the new one here. Okay, so you check Q P4, 2 zeros with 834. It is less than equal to V, so it's selected. So when P4 run and then allocate the request, so you need to minus first. Then when it finish, you remember that you need to read the process will return all the resources. So this is the last resources, last available resources, 836. Okay. After it's finished, what happened? After P4, then you go back to P1 here. Okay. Earlier, we cannot select this one because the available resources is less than the request. Yes, less than the request. Okay. So, but now we check QP1 again, 2222, which is smaller than equal to 836. So selected. Okay. So run the V. What you call, update the dynamic the available resources, okay, by request. Okay, and then when it finish, return all the resources. You have 936 here. Okay, I hope you understand. So just two steps. Okay, check with the available matrix, and then run into completions. Okay, and then return the resources and check the next one. Okay, you do until the next one, until you cannot do any anymore. Okay, and then this is how to check if your calculation is correct. You don't make mistake in the calculation. The available matrix, the last one will be equal to R. This is obvious, okay, because when you don't have any more process, the available will be the same like all the resources. Okay, so finally, then we can have now a safe sequence. Okay, the safe sequence in our case here, P2, P3, P4, P1. Okay, so this is safe. Okay, safe sequence. Okay, so what it tell you? It tells you that remember that on deadlock avoidance or in the resource allocation denial, it will try to simulate. Okay, so this is we don't allocate first. Actually, this is simulation. What if we do allocation, actual allocation? Okay, simulation, find safe sequence, and then we'll do actual allocation. Okay, so somehow we try to avoid the deadlock because you
Okay, so this time I just want to share to you the CPU scheduling, no, wherein this will be covered actually in the next topic, no. It is very important for us to know on how our operating system interacts with different functions simultaneously with other program. Okay, so good day everyone. Our topic for today, of course, is about operating systems, specifically the CPU or the central processing unit scheduling. So what is CPU scheduling? CPU scheduling is a process of determining which process will own CPU for execution while another process is on hold. So the main task of the CPU scheduling is to make sure that whenever the CPU remains idle, the OS at least select one of the processes available in the ready key for execution. The selection process will be carried out by the CPU scheduler. It selects one of the process in memory that are ready to execution. In the CPU scheduling, we have preemptive and non-preemptive as what we have here. Preemptive is the tasks are most assigned with their priorities. Sometimes, it is important to run a task with a higher priority before another lower priority task. Even if the lower priority task is still running, the lower priority task hold for some time and resumes when the higher priority task finishes its execution. On the other hand, non-preemptive scheduling, in this type of scheduling method, the CPU has been allocated to a specific process. The process that keeps the CPU busy will release the CPU either by switching context or terminating. It is the only method that can be used for various hardware platforms. That's because it doesn't need special hardware. For example, like timer and like preemptive scheduling. So, when scheduling is preemptive or non-preemptive, a process switches the running to the waiting state. As what we have here, a specific process switches from the running state to the ready state. A specific process switches from the waiting state to the ready state. And the process finished its execution and terminated. And only condition 1 and 4 apply, the scheduling is called non-preemptive. All other scheduling are preemptive. So important CPU scheduling terminologies. Of course, we have burst time or execution time, arrival time, finish time, multi-programming, jobs, users, process, CPU or input-output burst cycle. Now, we have here a scheduling criteria. We have a maximize and minimize. When we say maximize, that is CPU utilization throughput. On the other hand, minimize is a turnaround time, waiting time, and a response time. Maximize, the CPU utilization is the main task in which the operating system needs to make sure that CPU remains as busy as possible. It can range from 0 to 100%. However, for the RTOS, it can be ranged from 40% for low level, and 90% for the high level system. Throughput, the number of processes that finish their execution per unit time is known throughput. So when the CPU is busy executing that process, at the time, work is being done, and the work completed per unit time is called throughput. For the minimize, Waiting time is an amount that a specific process needs to wait in the ready queue. The response time, it is the amount of to time in which the process or the request was submitted until the first response is produced. Turnaround time is an amount of time to execute a specific process. It is the calculations of the total time spent waiting to get into the memory. So waiting in the key and executing on the CPU. The period between the time of process submission to the completion time is the turnaround time. The interval timer. Time interruption is a method that is closely related to preemption. So when a certain process gets the CPU allocation, a timer may be set to a specified interval. So both timer interruption and preemption force a process to return the CPU before its CPU burst is complete. Most of the multi-program operating systems use some form of a timer to prevent process from typing up or from tying up the system forever. So, what is dispatcher? It is a module that provides control to the CPU to the process. So the dispatcher should be fast so that it can run on every context switch. So display latency is the amount of time needed by the CPU scheduler to stop one process and start one another. So this will be the functions performed by the dispatcher. Context switching, switching to the user mode, and moving to the correct location in the newly loaded program. Now, we have the types of CPU scheduling algorithm. And as what we have FCFS, SJF, SRT, PS, RRS, and MLQS. So the first come first serve is the full form of course, FCFS. It is the easiest and most simple CPU scheduling algorithm. So in this type of algorithm, the process which requests the CPU gets the CPU allocation first. The schedule method can be managed with the first in, first out queue. As the process center the ready queue, its PCB or process control block is linked with the tail of the queue. So when CPU becomes free, it should be assigned to the process at the beginning of the queue or key. So this will be the characteristics of the FCFS method. The shortest remaining time. So the full burst of SRT is shortest remaining time. It is also known as shortest or SJF preemptive scheduling. In this method, the process will be allocated to the task which is closest to its completion. So this method prevents a newer ready state process from holding the completion of another process. And this will be the characteristics of the shortest remaining time. We have the priority-based scheduling. So this is the method of scheduling processes based on priority. In this method, the scheduler selects the task to work as per the priority. So priority scheduling also helps OS to involve priority assignments. The processes with higher priority should be carried out first, whereas jobs with equal priorities are carried out on a round robin or the first come first serve basis. So priority can be decided based on memory requirements, time requirements, and others. How about the round robin? So round robin is the oldest, simplest scheduling algorithm. So the name of this algorithm comes from the round robin principle, which where each person gets an equal share of something in turn. It is mostly used for scheduling algorithm in multitasking. So this algorithm method helps for starvation-free execution of processes. And this will be the characteristics of the round robin scheduling. Shortest job first. SJF is a full form of a shortest job first. It is a scheduling algorithm in which the process with the shortest execution time should be selected for execution next. This scheduling method can be preemptive or non-preemptive. It significantly reduces the average waiting time for other processes awaiting execution. And listed here is the characteristic of the shortest job first scheduling. Another, of course, is the multi-level key or queues scheduling. And this algorithm separates the ready queue or key into various separate keys or queues. In this method, processes are assigned to a key based on a specific property of the process, like the process priority, size of the memory, and others. However, this is not an independent scheduling OS algorithm, as it needs to use other types of algorithms in order to schedule the jobs. And listed here is the characteristics of multi-level keys, queue or keys scheduling. So, what will be the purpose of scheduling algorithm? So, the CPU uses scheduling to improve its efficiency. No, it helps you to allocate resources among competing processes. So the maximum utilization of CPU can be obtained with multi-programming, and the processes which are to be executed are in the ready queue. Again, the CPU scheduling is a process of determining which process will own CPU for execution while another process is on hold. In preemptive scheduling, the tasks are most assigned with their priorities. In non-preemptive scheduling method, the CPU has been allocated to a specific process. The burst time is the time required for the process to complete execution. It is also called running time. CPU utilization is the main task in which the operating system needs to ensure that the CPU remains as busy as possible. The number of processes that finish their execution per unit time is known throughput. So waiting time is an amount that a specific process needs to wait in the ready queue or key. So it is the amount of time in which the request was submitted until the first response is produced. Turnaround time is the amount of time to execute a specific process. On the other hand, time interruption is a method that is closely related to preemption. And a dispatcher is a module that provides control to the CPU to the process. Then, the sixth type of process scheduling algorithms, the first come first serve, shortest job first, shortest remaining time, priority scheduling, round robin, and multi-level queue scheduling. So in the first come first serve method, the process which requests the CPU gets the CPU allocation first. In the shortest remaining time, the process will be allocated to the task closest to its completion. The priority scheduling is the scheduler select the task to work as per the priority. And the round robin works on the principle where each person gets an equal share of something in turn. In the shortest job first, the shortest execution time should be selected for execution next. And the multi-level scheduling and method separate the ready key into various separate keys or queues in this method. Okay, processes are assigned to a queue based on a specific property. And take note, the CPU uses scheduling to improve its efficiency. So that's it. Thank you. And next meeting, we're going to discuss or where we're going to compute, no, on how we'll be able to get the first come first serve, shortest job first, priority, round robin, and others. Okay, so that this will be a CPU scheduling. I don't know the exact topic where covered the CPU scheduling. I think just within the uniprocessor scheduling, I think, no, yung mga computations and multiprocessor real-time scheduling. So doon tayo magkakaroon ng mga computations.